Basically, oil consumption measurement consists of two devices. I will just move over here. So on the one hand, we have the LubeSense analyzer system, which is the mass spectrometer, which the sole task of it will be to measure the SO2 concentration from the engine exhaust. Here, so the sole purpose for the mass spectrometer is to quantify the SO2 concentration from the engine exhaust. The way this works is we have different kind of operating agents in the engine. So we have air intake, we have fuel, and we have the oil. What we need to have is we have a certain quantified concentration of sulfur, which is in the oil, meaning that as soon as an oil consumption mechanism launches in the engine and oil is being either burned or scraped off the walls, it will enter the exhaust system. The thing is, we don't know which kind of sulfur components are in the oil. So it basically could be long chains. There are just sulfur molecules somewhere within the lubricating oil of the engine. So in order to have a signal which quantifies this sulfur content, we need our second device, which is the gas oxidizer. This is this device here, which is basically a high temperature furnace, which will convert all of the sulfur compounds which come from the engine oil and convert them by addition of oxygen into SO2. So first of all, we have compounds which contain sulfur that are pretty much unknown to us. And after passing through the gas oxidizer, these will all be converted into SO2. Then they will enter the instrument, and there the analysis of the SO2 concentration will proceed. So first of all, maybe I will pick up the camera and show you a little bit closer what is going on the instrument. So how to set this all up. So let's see if I can set it up properly. Yeah, that looks good. Okay, so this is actually, so we have rotated the instrument. So this is what we call the backside of the instrument. This is where all of the connections are. So what we will see here is we have main power supply, main power switch. Then we have on top here are all the calibration gas inlets. So in order to do the calibration for the SO2 measurement, we will have to provide a zero gas. This is usually, you see, this is one of these quick connector systems. All of these will come with the instrument, so you can attach them to a 1/4-inch Teflon. And the way they lock in is just to push them in, and then it is gas tight. So we will have a zero gas, which is nitrogen. We will have a spun calibration gas, which is typically a few ppm of SO2 that we use for the calibration of the sensitivity. And then you will see one special thing that I will touch on later is that what we actually do is we will pass these gases on this port, and this one goes to the outside. So I will explain this when I get to the function and principle of the gas oxidizer. Further on, we have here a heating connection for the so-called HPT. HPT in this case will be provided by Palmary, so that it is a heated extraction system for the exhaust. Next thing we have is the transfer capillary. So this one goes from the instrument up to the gas oxidizer, which is connected here. We have a heating system for the transfer capillary. This is the plug on the far right. And we have a heating system for this needle valve, which we use in order to set up a certain sample flow. As you see, the gas which is pumped here is going through a moisture trap and then going to the inside of the system to the sample pump. We have the possibility to have analog input and output signals. which means that there are 4 ports for analog out and 4 ports for analog in, where you can either feed signals into the instrument or take them out as a voltage reference, which is typically set to -10 to 10 volts, but can be adjusted as to the requirements on the test bench. The last 2 connections we have is here is Ethernet. So this is the one where we connect to the instrument. And the last 2 are down there. This is the sample out and the vacuum out ports. So since mass spectrometers operate in a high vacuum system, we have 2 outlets. So the vacuum out outlet is the one which comes from the high vacuum chamber, going to the turbo pump, pre-vacuum pump, and then coming out here. And the sample out port is the one which draws the gas from the engine exhaust system and has to be vented, of course, so not into the room, but you have to attach a line here and feed it into a venting system in order to not get excess CO2, which is usually present in an engine, into the ambient. The next part will be connections on the gas oxidizer. So again, we have a power supply, which is this white cable here in this case. We have a main circuit breaker for the furnace. We have 2 Ethernet ports. So these are bridged on a switch so that you can connect your PC to one port and then go from the other port to the instrument. And so both of the systems will always be physically in the same network. Then we have a connection for the 100% oxygen bottle. This is this one here. So in order to guarantee that we have full conversion of sulfur compounds into SO2, what we do is we supply a small amount of oxygen to the gas oxidizer, which will always be present in the sample gas stream, so that even when on the engine exhaust side there is no oxygen left, we still get oxygen for the sulfur conversion. What we still have here is another connection for heatings. And now I'm just moving to the front side. So like this. So what we're going to have here is the oxygen will be supplied to an ozone generator. This is the small box that is on the front here. This is there to, there are some sulfur compounds which are hard to convert into SO2, which is why we're using a small amount of ozone. This generates around 1,000 to 2,000 ppm of ozone, which enhances the conversion of the sulfur compounds into SO2. Secondary connection we have here is again a heating system for this front part. And what we see here is, so these are all just grids that protect from the hot part. So all of this will be very warm. We have one zone in the front, which is on 200 degrees. We have another zone in the back, which is 150 degrees. And here the main part will be at 1150 degrees inside. So it's, you can still put your hand close, but it is very hot, so take care of that. I'm going to just remove these protective grids in order to show you where the connections are made for the heated transfer lines. So here, this would be the front side of the gas oxidizer. So what I have done here is I have just put a T-piece like this so that we can provide gas to the gas oxidizer. In the final stage, when the system is equipped, we will remove the screws from this bracket. And then the heated line can come here and attach to the 1/4-inch port of the gas oxidizer. On the other side, we have already seen that. So we have to connect, just seeing that I'm getting it all on camera. So the transfer line from the gas oxidizer to the instrument, I can remove this grid as well. So you see here, this is a connection that comes pre-made. So it fits here on, again, a 1/4 inch swedge lock connection. And therefore, the whole system is finally set up. Okay, I will just put you back a little bit so that we have everything on screen again. Okay. So let me just quickly share my screen and go through the principal setup steps in order to connect to the instrument. Okay, so what we're going to have to do is the whole system will be controlled by our operational software. So this one is called V&F client, which we have here. So this is pretty much an intermediary window which will show all of the predefined connections to instruments that you will have. So in our case, we have a LubeSense instrument, which is the mass spectrometer, and we have the connection details here. So as you will see, you will always connect to the instrument via Ethernet. So you will have, the instrument will have an IP address, which will be entered here on the analyzer address, and you will have different users. So they are all documented in the analyzer records, which will allow you to connect to the system. Once you have entered these informations, you can click on connect. And this will bring you then to the main operator interface, which will control the instrument and also provide you with measurement data. So maybe just to give a brief overview what we have here. So we have here general instrument control, which means here I can set the system into measure. This is always indicated by the red dot. So right now, for example, it's standing in measure mode. We also have a standby mode and automatic calibration mode. The second part we have here is all of the signals that are acquired during the measurement routine. So for oil consumption measurement, we will have a measurement of water, a measurement of oxygen, and our most important molecule is the measurement of sulfur dioxide, which is SO2. And additionally, since the SO2 signal is only an indicator for the oil consumption, there are also secondary parameters necessary in order to calculate the actual value in grams per second. So the most important ones are the airflow. So this is the intake airflow of the engine and the fuel flow of the engine. These two parameters are provided by analog signals. So these are read by the analog inputs of the instrument that we have seen before. And we see here the final signal will be the oil consumption, which will be put out in a value of grams per hour. Here in the main window, we have general control of the measurement setup, as we call it. So we see here we have this drop-down menu, which has all of the methods that are currently on the instrument. So for oil consumption measurement, we typically have one method, and in this method, everything is set up in order to produce the values that we see here. Additionally, we can also control the gas oxidizer here in this lower line. So here right now, we see the gas oxidizer is currently in measurement mode, which means that our O2 supply for the gas oxidizer is running at 80 milliliters per minute, and our furnace temperature has been regulated to 1150 degrees Celsius. And the last part that we have up here is the choice of sample inlet. So if we click on this drop-down menu, we will see that we have an option which is called sample with pump. So this is the setting that you would use when you want to extract gas from the engine exhaust. And we have here these HPT settings for Cal 1, 2, 3, 4, and inert. these are the calibration gas inlets that we have seen before. So once I click on one of those, for example, I will choose HPT inert right now. This will open the nitrogen bottle, which is attached to the inert inlet of the system. So if I put this, what we should immediately see is, so this last window shows you live. So this is an online measurement. We have a time axis and we have a concentration axis. We should see an immediate change, for example, on oxygen, of course, because when we are drawing ambient air, there is like a load of oxygen. And if we draw nitrogen, there is less. This is what is reflected with the black line here. We still see, though, if we look at the value, the oxygen value is never zero in this state. The reason for that is because we are adding oxygen into the gas stream in order to have oxygen for conversion of the sulfur compounds. Same way, when I go back to sample with pump, the instrument will start drawing ambient air again. And of course, then, yeah, our oxygen level will rise back up. And also we see a little bit of moisture since nitrogen is dry and the ambient air typically has around 1% of moisture here in where we live. And the way this is going, I will just take the camera and follow the lines right now for you to see. So when I open the inert port, we see here there is nitrogen connected. So what will happen is the nitrogen valve will open and then supply the gas to this line here, which is connected to HPT. So the gas will flow in this direction. And once we follow that line, so I will just show it briefly, it's going down here and then will come back up here. So here the nitrogen will flow past this T-piece. So the instrument will just draw the nitrogen throughout the complete system. I'm sorry, now I've just messed it up. So this is very important for the calibration procedure, which I will take this away. This is all completely automated. So during operation, you won't have to take care of this, but it is very important to calibrate the instrument by using the calibration gas also throughout the complete measurement system. So through the gas oxidizer and then into the mass spectrometer. So set this up like this. Can maybe show one more thing. So as we see here, we have a few information on the gas flow and the furnace temperature. The gas oxidizer itself, on its backside, I will take the camera just briefly and move you around. So as you see here, there is also a small touchscreen on the gas oxidizer, which when you double tap it, will show you an overview of the system. So you see here temperatures of mixing chamber, furnace, and filter. You see the status of the oxygen flow, and you see the status of the ozone generator if it is switched on. This one is also available via a web interface. So as we see here, so this gas oxidizer has an IP address as well, meaning that what is displayed on the screen can also be accessed with usual web browser. So this is mainly for status. So you cannot really interact with it. This is just to get a visual representation of the gas oxidizer status. So now we can maybe go through the most important step. I will just place the camera back to the front. So once all the connections are made, the first thing that you will usually do, and I will do it manually right now, the automatic calibration routine will automate all the steps that I'm currently doing. Is we're gonna have to calibrate the instrument. So what is necessary for that? In principle, the two most important things to have is a 100% nitrogen gas to establish the zero levels of all the signals, and a calibration gas containing usually a single-digit ppm level of SO2. So now, the first step would be, okay, we want to establish the backgrounds. And as we have seen before, if I just introduce nitrogen like I did before, we will see the moisture and SO2 levels will be at the zero, but our oxygen level will of course not be, because we are adding oxygen by flushing the 100% oxygen gas to the ozone generator and then into the gas stream. So we will see here now we still have an offset of oxygen. So what we need to do therefore is, if we look into the sample preparation method, so these are pretty much the operating states of the gas oxidizer. There are two states here. We have a calibration with oxygen and we have a calibration without oxygen. So in order to establish the background for oxygen, we will have to switch to calibration without oxygen. If I do that, we will see two things. On the first hand, our gas flow will go to zero, and we will see that also our oxygen signal will go to zero. While you're doing this, you always have the options to, for example, save the data. I can also show this briefly. Usually the final data on the desk bench will be provided to some desk bench computer with analog signals, but we can do it briefly. So I can right click on the method here. I can go to the point edit setup, which will pretty much give me the complete configuration of this method. And we have here one tab, which is called options. And here on the downward part, I can choose a folder and I can choose a file name if I want to manually save data. So I will go here to the desktop folder. We will call this test. Confirm this with OK. And in order to start and stop a save of a file, we will need these two buttons on top of the general control part of this window. And we will start to save by pressing here on save. As you see, the red dot appears, meaning that right now we have started to create this file here. What happens then is each subsequent measurement will be written into this file, which is plain text. So it can be read by either a text editor, by Excel, or by any program. And while I'm saving, if I want to make notes, which are pretty much text-based indicators of what I have done, I can click up here. I can add a note. What I've done here is, for example, I have done calibration without O2 and running 100% nitrogen. And you see these nodes will be attached into the timeline, and I can look at them either by double clicking here or later on also in the saved file to see what's going on. So the next step would be to establish the background level. I'm doing all of this manually right now, just for you to get an impression of what is being done. The automatic calibration routine will do all of this by itself. So if you right click on these molecules, we will have a calibration option here. And for each molecule, we will have two options. We have a background calibration and we will have a span calibration. So the background calibration will use the current measurement data which is acquired in order to establish the background level. So before doing a background calibration, what has to be done is you have to supply the nitrogen. The gas oxidizer needs to be put into the correct state. meaning that right now we pretty much have zero signal. And then I can click here, and I will just by one click see that when I do this for all the molecules, that the backgrounds will be established. Then the next step would be is we want to look at the spun value for oxygen. In order to do that, we will keep the instrument, the gas oxidizer, on calibration without O2. And since I don't have a certified concentration here, I will just use ambient air right now. So I will switch the system to sample with pump, meaning that now the gas will be drawn in from this side, and we will see that we get an oxygen signal right now. So we will give the instrument a few measurement cycles so that we have enough points to perform a spun calibration. So we know that in the ambient air oxygen, the level is 20.8%. So what I'm going to do is I'm going to click here, right on the oxygen molecule, then go to calibration. And now I will select the spun calibration option. And of course, since the analyzer doesn't know which gas is currently attached, I will have to give it the correct concentration. So in this case, I will enter 20.8 volume %, and then I will confirm this step with OK. So we see here there was a small jump in the signal, resulting in the correct spun calibration. And again, what I can do is, in order to know what I have done, I can say what I did was calibration without O2, ambient air. Then I did an O2 spun calibration. Okay, so that was the first step for oxygen. Now for SO2, one thing is important. Before we can calibrate SO2, we have to set up the measurement flow throughout the system. Meaning, I will set the system, so the gas oxidizer, to measure. What will happen is we see, all right, the gas flow of the 100% oxygen bottle is being established. Therefore, we are also getting an increase in the oxygen signal itself. And what we want to do is the following. I will show this in step by step. We have already established the calibration for oxygen, and we know we are having an 80 milliliter per minute flow, which is introduced into the sample gas stream. So what I'm going to do now is I'm going to switch again to HPT inert, which is where our nitrogen is attached. And as we see now, what we have is we see an excess oxygen of 9 volume %. And this is actually the correct state it should be in, because I've already set it up. But I will go now and I will detune it and show you what is going to happen. So the way to set up the gas flow through the system is by a component that we have seen earlier before. This is the needle valve that we have down here. So this is this one. So this is mainly there to restrict the full pumping efficiency of the sample gas pump, which is in the instrument. So what I'm going to do now is I will just artificially open this needle valve so that there is more flow through the system. And what you should see on the signal, that the oxygen signal has now decreased. This is because the oxygen flow that is supplied into the sample gas stream is constant. So if I increase the volume that is pumped, then these 80 milliliters will amount to a lower concentration because they are mixed together. So once you have done the oxygen calibration, you should always check, while the gas oxidizer is in measure mode, that the oxygen value that you get for 100% nitrogen gas is at around 10 volume%. And like it is now, this is not the case. So right now we only have 7.4, 7.2%. Meaning what you will have to do is you will keep the system in this state, and then you will set up the flow on the needle valve. So what I'm going to do is I'm going to try to close the needle valve. So this is a clockwise direction movement. And after doing this, I will check again where our oxygen level lies. So as far as I see right now, we are still at 8 volume%. So we still have to close it a little bit more. I will do this again. So clockwise motion. Okay, we have another small increase. So we're going to 8.1. The thing is, this step is pretty much necessary for the initial setup. Once you have put the needle valve to the correct position, this usually stays the same, but it's always good to do a checkup. So as you see, I'm closing and closing and closing until I will reach the 10% value. This is not really a completely exact necessity, but it is the way that we use that the system works optimally. Okay, so this pretty much means that right now we have reduced the sample gas flow to roughly 1 liter per minute. And this is also necessary because if you have too much gas going through the gas oxidizer, then conversion efficiency will drop, meaning that this setting is important to make. So do I have everything on there again? Yeah, like this. All right, so once we have done that, then the last step will be is to calibrate the SO2 sensitivity. And this is also important. This needs to be done while the system is in the measure mode. So everything needs to be running in order to get the SO2 calibration correctly. I have an SO2 calibration gas connected to the HPT Cal1 port. So by selecting it, I will flush this gas to the instrument now. And what we should see is that, forgot to take the note again. So previously set up needle valve for sample gas flow. And I will put another note now, apply HPT Cal1 SO2 calibration gas. And so what we see here now, of course, on the SO2 calibration gas, what we expect is to get a response on SO2, which is coming along nicely right now. So this is the red line here. And again, we're gonna have to flush the gas for a little time. And once the signal saturates, we can do the same procedure as we did before on the oxygen signal. So we're gonna right click, and then we're gonna select the calibration tab, and then we're gonna select the span calibration. And in this case, we have an SO2 calibration gas of 2 ppm. So this value is already correct, but we're still gonna do it. And that is pretty much everything that needs to be done. So after this calibration step, the measurement can proceed. I would like to show you how this is done in an automatic way. So if we look at the definition of this measurement method again, I will go here by right clicking and then edit setup. We see that we have here a tab which is called calibration. And so these are pretty much all the steps that I have gone through manually right now, but they are done in an automatic way. So you see here we have a first step, which is a background calibration using the HPT inert inlet and the gas oxidizer setting calibration without O2. And what I can set up in this tab is a purge time. So this is basically a time that it takes when you switch on the gas until the signal saturates. So usually a setting of 2 minutes is sufficient for that. Then you will define the amount of measurement cycles you will use in order to produce your background values. And here we have a maximum deviation, and maximum tries is pretty much the instrument will check if there is too much internal deviation in the measurement. It will trigger an error, but it will only do so after trying it 2 times. So this calibration step can run up to 2 times. And if there is something wrong during the calibration, the instrument will report an error. And as you see here, we have the second step would be the oxygen calibration, which is in this case, it's a spun calibration on a sample preparation calibration without O2. And our default method is to have an oxygen, like a synthetic air on a HPT Cal1. This is, unfortunately, I don't have that bottle here right now. So my setup is currently a little bit tilted. So because here the SO2 calibration will use calibration with O2, which is the same as the measurement state for the gas oxidizer. And usually the SO2 calibration gas will be connected to the HPT Cal2 port. But this is all documented in the auxiliary materials that we provide. And in order to launch this routine, this can be done by using the calibrate button. So if I click on this one, the instrument will suggest to me which kinds of calibration steps I want to run. So usually what is done is we are going to run all of these calibration steps. Right now, I'm sorry for that. I have set it up in a wrong way. But basically what happens is everything that we have done manually before will be done automatically. So I can probably just set it up briefly. So once we start this, maybe you can keep your eyes on this part. So when I start this, we will see that all the sample inlets, the gas flow, and the sample preparation methods will switch automatically. So the only thing that you need to take care of is that the correct gases are supplied to the mass spectrometer. So once I start, we will see, all right, what has happened now is the system will launch the HPT inert mode. So now nitrogen is supplied to the instrument, and it will automatically switch the sample preparation to calibration without O2. And we can follow what is going on the calibration routine by looking at this status here. So right now, the system is running a delay mode, and this is pretty much the flush time that has been set up in the calibration step. So right now, the instrument will go through 2 minutes of flushing the gas, and then it will continue with 10 measurement cycles in order to establish the background value again. After doing this, it will go to the next step. So this would be, as you see, usually we suggest to the customers to supply either synthetic air or industrial air from a compressor to the Cal1 port. And once this step is done, the instrument will go to the SO2 calibration step, which will then do the spun calibration for SO2. And once you have run this automatic calibration routine, this will have the instrument in a ready state where you can then commence with the measurement on the engine. And for oil consumption, I will just leave this running in the background. There is an additional very important step which needs to be undertaken on the test bench. And this is pretty much the last thing, but also the most crucial thing in order to get the oil consumption measurement right. So we've talked about it a little bit before. we need to have information what is going on the engine in order to be able to calculate the oil consumption from the SO2 signal. And these informations come in the form of airflow and fuel flow. I will right-click those and click on properties here. So you see here these, in the method, we have 3 molecules that are measured by the mass spectrometer. And we have here, actually there are 4 analog inputs, but the most important ones are airflow and fuel flow. So as you see here, we need to set up the system in a way that we supply a corresponding airflow signal from an airflow meter to the analog in 1 on the system. And we need to supply an adequate fuel flow signal to the analog input 2. And this now always has to be matched with the voltages that are being put out by the airflow meter and the fuel flow meter. So as we see here, the unit that we need is kilograms per hour. That is also important. So if the airflow and fuel flow meters will provide a different unit, then the conversion needs to be done correctly so that the system is supplied these 2 values in kilograms per hour. Why is that? Because oil consumption basically is correlated with SO2, but it will also be correlated with the fuel flow and airflow of the state in which the engine is running. So what we see here is this is a very basic representation of this calculation. This is done in an old reverse Polish notation, which is a historical artifact for us. But as you see, we will have operands here which use the actual fuel flow and the actual airflow of the engine in order to produce the final value for the oil consumption. The exact formula is also provided in our auxiliary materials, so where it has a little bit of a more nice representation. But the most important step for every oil consumption measurement is the following. We will need to know the sulfur concentration in your fuel, then sulfur concentration in the air, which is usually at 0, and also the sulfur concentration in the oil, because these are like our basic steps or our basic parameters in order to correlate the concentration of SO2 that we measure in the system to the actual oil consumption, which comes from the engine oil. So the sulfur level in the oil and sulfur level in the fuel are 2 important parameters to know. If the oil and fuel that you are using do not come with a specified sulfur content, then samples of those will have to be sent to a lab where total sulfur analysis can proceed. And once you get those results, you will have to do exactly what I have just done right now. So you will have to go, I can directly go to the oil consumption molecule here. I will go to properties, and then you will have to find these 2 parameters in the formula. So here we have S in fuel, which is usually very low. This value is done in ppm weight, as you see here. So this would be like a 1.5 ppm weight sulfur fuel. And we're going to use here sulfur in oil, again, is entered in ppm weight. And you will have to set it to the result of your engine oil that you are using. So per standard, we usually enter 10,000 here, but it needs to be modified according to the results from your lab. And so now what will happen is, since unfortunately we don't have an engine here in order to try it out completely, what will happen is the test bench computer will provide airflow, fuel flow to the instrument. The instrument will measure the SO2 content in the exhaust gas and will provide an oil consumption value. And then this one, we can also check this out again. I will go to properties. This one will be provided on the analog output port 1. So another BNC cable will go back to the test bench. I'm just looking if there is, yeah, and if the concept of analog signals is not the way you want to do things, we see here that the instrument also has the possibility to be controlled with AK protocol, meaning that if you don't want to rely on analog signals, you can always do it the other way around, meaning that the test bench computer will have an AK driver which talks with the instrument. And here it's going a little bit differently. So customers usually do it in a way where they will only read the SO2 signal via AK and then do the calculation on the test bench computer. So I can also refer again to the auxiliary materials so that the formula can be implemented quite easily in a test bench environment. And the more convenient part for this is that you will have the airflow and fuel flow values from the test bench available, and you only need to set the two constant parameters, which is sulfur in oil, sulfur in fuel, and you only need to read the SO2 value from the measurement system, and then you can do the calculation on the test bench computer. So as we see here, our calibration process has been running in the background now. So this takes roughly, with the settings we have, about 10 minutes in order for you to get the system ready calibration-wise. So here we have 3 steps are already done. So this was the background calibration and the 2 span calibrations. And now this last step is basically just flushing industrial air to purge all the lines. And once this process is done, you can pretty much commence with your measurement. Okay, so this would be pretty much it from my side for a first demonstration of the instrument. If there are any questions right now, I think we can open it up for discussion. And for you is the perfect time to ask any questions if you have them.